In the last video, we reviewed the mathematics of exponential decay in the context of first-order chemical kinetics. Let's use these mathematics to get some practice with vectors in R and to look at the results of calculations with these kinetic models. First, I'm going to go ahead and start up a new R script. And as usual, at the top, I'm going to add rm list equals ls. And I only have this in here when I'm actively developing a script. It just helps to make sure that the global environment gets cleared out every once in a while. Make sure that there's nothing in this script that depends on something already being in the global environment. If I want to do a thought experiment about a reaction, let's say I know a reaction takes about an hour for me to see the meaningful completion of a given reaction that might be occurring. That might mean I need a vector representing time in R that represents time over the course of an hour. So I can create a vector of values. I'm going to call the variable t here for time, and I'm going to assign to that variable a vector that comes back from the seq, or the sequence function. I'm going to pass the argument from, I want to start at time 0, and I'm going to go to 60 minutes, so I'm going to use units of minutes here. So from 0 to 60, and I want to count by 1. So I'm going to create a vector where I have values that increment by 1 for each element of the vector. So if I go ahead and I run this script, I should see that I have a t with values starting at 0 and incrementing. You can see that here in my global environment, in the environment window in RStudio. I can also go to my console and type a t, and then I see indeed I do have a vector. I think you'll find that there are 61 total values here because it includes 0. And it goes from 0 to 60 in increments of 1. So now I have a vector of times that represents the time of my experiment. I can go ahead and do my calculations with my kinetic model. In this case, I'm doing an exponential decay, so one variable that I'll need is the initial concentration. I'm going to call this C0, or C lowercase o for C0. That's indicating the initial concentration. And let's say for this reaction, we know our initial concentration of a reactant is 100 milligrams per liter. This is a first-order kinetic situation, so we know we need a Kr, or a first-order rate coefficient. And I'm going to assign the Kr to this case, in this case, to be 0.1. That's based on the idea that there's going to be a certain amount per minute that I'm reducing that initial concentration by some fraction. In this case, I want to say that every minute I'm going to reduce the concentration by 10%. So that's the continuous rate I'm going to be applying. So those are the two parameters I need to define this model. Now I can do a little bit of math to see what the concentration must be at each of the times I have in the vector that I created. So I can use vector mathematics in R to do that. R is designed to do math with vectors automatically. So I'm going to call this C for concentration of my reactant. And then I'm going to say, well, my initial concentration is C0. And that's going to be multiplied by Euler's number raised to KRT. In R, the way you can specify the exponent for a natural log is with the exp function. So I'm going to call the function exp, and that's the same thing as raising the Euler's number to some exponent. And then inside those parentheses, I want to pass the argument that is my exponent, and that's going to be Kr multiplied by t. Now notice here that vector math automatically gets applied. Kr is a vector with just a single element, the value 0.1. But t is a vector of values with 61 values in it. But R can handle that. It'll take this 0.1 and multiply it by all of the t's that are in there and provide that vector as a value. Exponent will be that vector, so the exponent of that will be a vector. The exponent of each one of those values of Kr's time t, that vector. And C0, again, is a single value, but we want to multiply that C0 by all of the values in that vector. So ultimately, we know from this math that our C will be a vector that's the same length as our original t, and each value will be the result of the math that's being provided here with these parameter values. So we can again run all of this and we can look at what our C looks like. Again, we see it's a vector. I'm going to type it in the console here. And at 0, our first value, we're going to be at 100. That's our initial C. And for each time step or each minute through here, we can see that if we continuously apply a 10% per minute decay of this reactant, these are the values that we'll see. So that's a quick overview of how we create vectors and how we can do vector math in R. Now that we have those values, it'd be nice if we could visualize what those values look like. So let's learn how to make a plot in R using base R graphics. So first of all, if I want to open up the graphics in a new window, I need to open up a new graphics device. If I didn't do that, then it would show up down here in the bottom right on this plots tab. But this plots tab is going to have an aspect ratio that depends on how I have RStudio set up. I would rather see my graph with an aspect ratio that I control and a size that I can control, just so that I have some control over that. And this is especially important if you're making publication-ready graphs later on. But in Windows, if you're using a Microsoft machine, the device you want to open up to see graphs in a new window is the Windows function. And two arguments that you commonly want to set in Windows are the width of the window. This would be in inches, and this is going to depend on how you have your resolution set up on your monitor. But I find that it will show up with a nice size on my monitor if I make the width of 8, and I'm going to call the height of my window 6. Now, if you are on a Mac machine, you can do the same thing, but the function you call instead of Windows is quartz. So I'll go ahead and type this in, but I'm going to comment it out because it won't work on this Windows computer. So you're going to want one or other of these lines of code. If you're on a Mac, you'll use quartz. If you're on a Windows machine, you'll use Windows. Now, it's very easy to get a plot started with a basic bivariate plot in base R graphics. There's a function you can call called plot, and the arguments to plot are whatever vector you want representing the values on your x-axis. In this case, we want to plot concentration versus time, so our x-axis should be t. And then you can give it a vector of values for your y-axis as a second argument. In this case, that's going to be c. We're plotting concentration on the y-axis versus time on the x-axis. So this is really all you need to get started with graphing in R. I'm going to click source here, run my code, and my window popped up in the background, but if I click here on this window, I'll see my pop-up window that this code created. I have an axis. By default, it called the axis C because that's the name of the variable that I'm plotting. And likewise for my x-axis, by default, it called it t because that's the variable that I'm plotting. And you can see I'm going from 100 following an exponential decay at a rate of 10% per minute relative to the concentration of my reactant declining over time with respect to t. So that's just a quick script to get some practice with actually making real vectors that mean something and then plotting the results and visualizing that.